Digital signal processing is an application of linear algebra to our discrete time signal behavior. My favorite version of this was digitizing analog EKGs. I worked for a pacemaker company over the summer. They gathered EKGs on an analog piece of equipment, which made 1,000 samples a second. They were converting to digital equipment, which did 1,024 samples a second. It means we had to do a bunch of linear interpolation. That is a linear transformation. So, turns out, did this, but it was in the 90s, and that was a long time ago, and we did it by hand. Very, very, very tedious process. But if I want to work on signal processing, I need a library of signals to work for. So in the textbook, we have a table of a bunch of useful signals that we will see in several distinct places as having utility. The delta signal is a single ping, and it just goes off once. It's 0 everywhere else, and it's 1 here. Now, it's kind of hard to see. I need some indicator of time across this signal. And they've put at the bottom here that this is the point 0. So in all of these, this occurrence is t equals 0. So t goes to the negative on to the left and to the positive on the right, counted by integers. That's our signal space, the same way we were doing it for S, right? What we call our signal space. Funky looking S. Okay. So a delta is, hey, I'm here. I'm 1 only at time 0 and 0 everywhere else. The unit step turns on at time 0. It goes from being 0 to being 1. This is the discrete version of something called the Heaviside function, which we did in Calc 1 when we talked about limits from 2 different directions. Same exact function. Same function we used in differential equations to talk about engaging a cycle or starting a force. We're going to use the Greek letter nu, this little V shape here, for the unit step. A constant function. 1, 1, 1, 1, 1, 1. It's kind of boring, but there it is. An alternating signal, which flips between -1 and 1. This signal is based on the Fibonacci sequence. As we go to the right, we follow that same recurrence relation by adding the 2 previous ones that went before it. But as we go left, we subtract. So it turns out the numbers on the left are negatives alternating, it's plus minus as we go to the left, of the versions of the numbers on the right. So here, the next number to the right would be a 3. We add the 1 and the 2. Here, it would be -1 minus 2, so I'd get a -3. Then the number after that would be 2 minus -3 would be a +5, whereas over here we get all positives all the time. Exponentials. I take whatever constant I want. I raise it to integer powers as I go to the right, negative integer powers as I go to the left. This is a discrete version of the graph of e to the x, or c to the x, what this is. And then I can include things like periodic signals. Wait a minute, what's it mean for a signal to be periodic? It means for a function to be periodic. Trig was a long time ago. Periodic functions. So that would definitely be a sine wave, but periodic functions don't have to just look like waves. They could look like anything. Then it wouldn't be a function, right? Because it wouldn't pass the vertical line test. So it definitely can't do that, because if it's not a function, It has to only have one y value for each x value every time. But you said within a certain section, right? It's that repeating idea. If whatever this q value is, I repeat this often. Now, if I'm dealing with a discrete time signal, remember our discrete signals are sequences of real numbers, right? So if I have a signal that is periodic, then instead of using discrete, I forgot the word discrete. I want that same behavior. I want that repetition every q subscripts. Now, Shane, if I really want to make a wave, I could pick something like, say, sine of x, and I could say we will create a family of signals. Something like this. That should have another set of parentheses. Sorry. This is some sort of a cosine. And since I'm multiplying and adding inside there, I've really got a cosine that's either squeezed or stretched, and then it's shifted a little bit to the left or the right. This could be a whole, for different values of f and theta, this could be a whole different set of pictures based on my choice. So, for example, there. This figure is absolutely a periodic function. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Look, it repeats every 12. Add 12, and you get exactly the same y value every time. So there's that q value I was talking about in the first place. This repeats with a period of 12. Now, in this case, it's because there's a pi over 6 there, and the period of cosine is 2 pi. 2 pi divided by pi over 6. Oh, right, that's 2 over 1/6, which is 2 times 6, which is 12. Sneaky mother, I remember that, but trig was a long time ago. And then this is a phase shift. We talked about being in phase or out of phase back then as well. Now, periodic signals come into play a lot when you're trying to transmit radio data, signaling information, location data. Those pings come out all the time as periodic functions. I want to talk about transformations on these vectors, because remember, S is a vector space. So if I have some of my vectors here, things that look like this, I can ask, what can I do to them? Can I find a way to generate a signal by using some combination of basic symbols? Wait a minute. Sounds exactly like creating a basis for a vector space, doesn't it? If I can start with one vector and use it by transforming it into all of these other vectors, I can store a basis vector and then build by transforming any vector I want. So I'm going to define a couple transformations, and then I'm going to describe some properties that I want my transformations to hold. Here, transformation called S. S stands for shift. This is a one shift to the right. In assembler, this is called an arithmetic shift right, ASR. But what that means is that S of YK, the signal, moves one unit over. Now, what is it? What the S of YK equals brace YK minus 1? Here's my original signal. Remember, that's what a signal looks like as a discrete time signal. That's what goes in. I'm going to do S to this, and I'm going to get out another signal. And what it says there is that YK in the new signal be YK minus 1 in the previous signal. So remember, we have indices lined up. So this is K equals minus 3, K equals minus 2, K equals minus 1, K equals 0 and 1 and 2 and 3. Right? So here, that's K equals 0. What thing should go where that dot is? This item. See how we shifted it to the right? And this is K equals 1. The thing that should go there is Y0. Everything shifted right by one place. So, based on that idea, what is S of delta? Remember, I started with that list out of the textbook of basic signals. We need this list. So grab your textbook, open it up, table 1 in chapter 4, section 7. What is the signal delta?
Instead of the 1 being in the middle and then all the zeros, would it be shifted over to the right by like 1 unit?
Exactly. So I used a little underline to mark the 0 spot. If this is where k equals 0, then I shifted it one spot to the right. Let's do it more than once. What's S of delta? Actually, I'm going to cheat. I'm going to write this as S squared of delta. I did S twice.
Push everything to the, wait. Inclined to say twice, but there's also exponential.
No, I'm just moving delta, right?
Oh, okay.
To the shift, I'm doing the shift to delta. But it says do the shift twice. So I move over, and then I move over again. I can think of this as a function, right? We have a list of numbers, a list of spots, and then we have another list of spots, and we're figuring out where we move stuff, right? This is one-to-one. Every spot gets moved to a different spot, right? And we hit all the spots, makes it not only one-to-one, makes it onto, which makes it invertible. What would S inverse do? It would go to the left. It'd move the other way. I suppose if I really wanted to be pedantic, I could jump to the left and then we could do the time warp. But what that means is that I could do that as many times as I want, right? Just like I did it twice here, I could do it 3 times, 4 times. I could go as far left or as far right as I want and build a signal with a 1 anywhere I needed it from just one basic signal, delta, and one shift operator. If it's a claim, it needs to be verified. I should prove this. How do I prove that something is a linear transformation? I know how to prove it with matrices and vectors and arrows and shit, but what do I do here?
Would be fine at inverse, I guess.
Well, finding the inverse just tells me it's invertible. How do I prove that it's linear? Closure. I don't actually need the zero because that part is about subspaces, right? I'm looking at the transformation. There were two properties I needed to show. Now here I've written them as vectors because this property, this is the definition of what it means for a transformation to be linear in any vector space. This is from last Wednesday. Sorry, Wednesday before because we had break. I know, it leaked out your ears. We'll find it again. But I want to show this is true for this function S, which operates on signals. So, that is the left-hand side. When you're adding signals, you just add the corresponding entries, right? So that means that what I'm really doing is I'm doing the shift of the signal whose pieces are xk plus yk. But that is shift 1 unit right, yes? That is xk minus 1 plus yk minus 1. Came over this way. I just did it to both of them at the same time, yes? Well, let's do it independently. Let's look at the right-hand side. S of xk plus S of yk. What's S of xk? We wrote it down earlier. That's only if I know it's 0 to begin with. S is a signal, right? It's a transformation of a signal. I don't know what the signal is. Might be 0, might be something else. This comes from moving over 1. What about this one? And when you add two signals, what do you do with the entries? Isn't that going to give me the same thing I got right here? So these two things are equal. That checks off box number 1. When you do a scalar multiple, you multiply each thing in the signal, right? So the left-hand side of this says multiply each thing in the signal. So everything in the signal just got multiplied by C. It went up or down or it got shrunk, whatever, it just got multiplied. But now I shift that, and that gives me the xk minus 1 part. But notice every number in that signal has a c in it, yes? Look at the right-hand side. C times S xk. What's the shift do? That's what our shift does. And then I take this C and I multiply it in and I get that, don't I? And that's check number 2. This is a linear transformation. But it turns out that there's another property that this shift has. This shift has what we call time invariance. And our shift is actually a measure of time invariance. It's how far we moved the signal down the road, yes? Being time invariant means I can delay my signal and it will simply delay the output. Key here is how far we pushed our signal down the line. I think I used Q earlier for a delay, same idea. If we have not only the first two properties, but we also have this one, we have what's called a linear time invariant transformation. A linear time invariant transformation is a special kind of a linear transformation. It's got to have all three of these properties. Definition in the big box, blue box, above something called Theorem 16. In my book, it's on page 257. Please notice the first two are exactly the properties we wrote for any linear transformation. We're adding this extra one. There's that delay piece. But if this is a linear transformation, that means I can work with questions about the range, the kernel, what things get mapped to 0, what's the image of a particular vector. Oh, I can now do all sorts of interesting things, and I can ask you about other kinds of transformations and ask, are these transformations linear time invariant? Here's a transformation. Now, what does this do to a particular signal? This turns my signal into the difference between each pair of terms. Instead of taking the signal, I'm now asking you, how much did it change from each step to the next? If I knew where it started, I could thus tell you where it is, right? How far up or down it went. So if my original signal was a set of stock prices, what I've got is the change in that price every day. Gee, where am I going to use something like that? Modern marketing every freaking day. Or maybe it's website traffic. Did I gain or lose traffic each and every day, each hour? What's my throughput? What's my number of site visits? Distinct number of visitors entering this website on a given time period. I don't do network trafficking. I'm not an IT manager. Somebody does. Somebody gets paid pretty damn well to do that sort of stuff too. Is this a linear time invariant transformation? Find out. Now, a lot of this is simply symbol manipulation at this point. Let's start with the left-hand side. T of xk plus yk. Well, that says add the two signals. Before I do the transformation. Transformation says you take the kth one and subtract the one before it. With me so far? Group these. Group the x's, group the y's. What would you have? When I rearrange to put the x's together and the y's together, what do I get?
xk minus xk plus yk minus.
Perfect. But notice, that's two things added together, right? Which means I could make it two separate signals, couldn't I? That should be a minus sign there. But wait a second. What's this? And if that's true, what's this? Isn't that what I wanted to show was true? Yay! There's one. it now shows that I can add before or after, and I'll get the same result. How about property 2? Property 2 asks, is t of c times my signal equal to c times t of my signal? So start on the left and manipulate, and let's see if we can get to the thing on the right. So I multiply the signal by the constant. Then I do t to that. What does t do? Say again?
Cx k minus 1.
My transformation itself is the subtraction of two things. I need xk minus 1, but I also need xk in there, right?
Yeah.
And both of those will have c's on them. What can I do with the c? I absolutely can. I can factor it all the way out. And then this is the result of doing the transformation of the x's. That's exactly what I wanted it to be. Showing the time invariance means comparing the output and the input down the road. So that's what our transformation does. It takes each number and subtracts the one that came before it. If I delay my signal, so let's add something to our subscript. Well, all that's going to do is it's going to take that entry and subtract the one that came before it. Yes? If I delay my signal, I delay the output by exactly the same amount. That's what time invariance means. The pause button. There are non-time invariant signals. Compression behavior would not be time invariant. This is literally a shift down the line. So yes, we've hit all three. This is an LTI. That means it's a linear transformation. That means it's got a kernel. Somebody remind me what a kernel is? What is the kernel of a transformation? It's the set of things that get transformed to 0. So, if my transformation is this, what's going to force that output to be 0? And that's got to be true everywhere, right? What does that make my signal look like off my basic list? A constant. So the things that don't change when you shift them, that's what this does. It measures how much it changes every time we move over one. That change is always 0, then I never changed. It must be the same value all the way across. It doesn't have to be all ones. It could be anything. But that means that I know the kernel is a subspace. Kernel of a transformation is always a subspace. Because this is built off that one vector, it's a one-dimensional subspace. The set of constant signals is the set. What was the letter we gave our constant signals? I have my table here. The constant signals were a chi for constant. We did averages. If you take two sequential terms and average them, so instead of just subtracting, take xk plus xk minus 1 and divide by 2. That's a running average. It averages each two terms together. Please notice that the running average is less jagged than the original data set, isn't it? That's a smoothing filter, a noise reduction filter. And it doesn't have to be audio, but it sure as hell could be, couldn't it? Artificial audio is generated to sound real by enhancing the noise. It means if I have the filter to reduce it and I can find its inverse, I can generate noisier signals. I can lopside them if I can figure out how to bring them together. I can figure out how to cut them apart. I can make better sounding audio this way. Ladies and gentlemen, I give you audio deepfakes, whose basis is the voice I start with. And then I add all the right artificial noise pieces. Now, I will say that there are lots of other subspaces of the signal space. One of the most important, in my opinion, is the finite signal space. Signals of length n. So they only have the potential for non-zero numbers from x0 to xn. My signal looks like that. This is isomorphic to Rn plus 1. Because each vector has n plus 1 entries at most that are non-zero. On the other hand, if we consider the set of signals that have at most a finite number of non-zero entries, technically that is not a finite dimensional subspace. Theorem 17 and 18 in our text talk about the way in which we build the bases for these spaces. Modern signal analysis is based off of this foundational idea. I don't care what sort of signal processing you're doing. This is at the heart of it. And that means things like codecs and general compression algorithms and Therefore, general data analysis is in some sense a linear algebra problem. This ends the material I want to cover in chapter 4. And that means we've covered a crap ton of material. And that means we shouldn't cover any more before I add an exam to this pile, because otherwise the exam gets uglier and uglier. So we're going to have an exam, and it's going to cover through today. That means the exam is a week from today because this assignment is due Friday. The review sheet is already on Canvas. Come ask me if you have questions. I will see you on Wednesday. Have a wonderful day.